Here's an equation that looks innocent at first, but there are some genuine surprises waiting. We want to find all real solutions to 6 to the power of x equals x to the 18th power. And as we'll see, the complete answer requires us to be quite careful. The key insight is that this equation behaves very differently depending on whether x is positive or negative. So our strategy will be to split this into cases and handle each one systematically. Before diving into cases, let's quickly check whether x equals 0 might work. 6 to the power of 0 is 1, but 0 to the 18th power is 0. Since 1 doesn't equal 0, we can rule out x equals 0. Let's start with the case where x is positive. Starting with our equation, we'd like to find a way to isolate x. One natural approach is to take the 18th root of both sides to undo this 18th power. In other words, we're raising both sides to the power of 1/18. Now, here's where we need to be careful. In general, when you take the 18th root of x to the 18th power, you get the absolute value of x. But since we're assuming x is positive in this case, the absolute value of x is just x itself. So we can simplify our equation to this much nicer form. Now, let's try to find an integer solution. Since the base is 6, it makes sense to try values related to 6. What about 36? When we substitute 36 for x, the exponent becomes 36 divided by 18, which gives us 2. And since 6 squared equals 36, we've got a perfect match. There's our first solution. So x equals 36 is our first solution. Now, a natural question: are there other positive solutions hiding out there? Here's the challenge. This equation is what mathematicians call transcendental. The variable x appears both inside an exponent and by itself. Unlike polynomial equations, there's no algebraic formula that can solve this. We need to use graphical analysis and numerical methods. We'll plot both sides of our simplified equation to see what's happening. The solutions we're looking for are where these two curves intersect. Where the line y equals x meets the exponential curve y equals 6 to the power of x over 18. And look at that. The graph reveals two intersection points. There's our solution at 36, and there's another one near 1. The graph alone tells us it exists and is approximately 1.12. Now, if you're satisfied knowing the solution exists from the graph, feel free to skip ahead. But for those curious about how to compute it precisely, let me show you the Newton-Raphson method. This is the tool mathematicians and engineers use to solve transcendental equations. To solve this precisely, we'll use the Newton-Raphson method. This powerful numerical technique uses calculus to iteratively find solutions to transcendental equations. We rewrite our equation as f of x equals 6 to the x over 18 minus x, and we're looking for where this equals 0. Taking the derivative using the chain rule, we get the natural log of 6 over 18 times 6 to the x over 18 minus 1. The Newton-Raphson formula updates our guess by subtracting the function value divided by its derivative. Substituting our specific function and derivative, this is the iteration formula. Let's watch it converge. Starting with an initial guess of 1, the first iteration gives us 1.117. After just 3 iterations, we've converged to 1.1180. This is the power of Newton-Raphson. But how can we be sure there are exactly 2 positive solutions and no more? Let's think about the behavior of these functions. Here's the key. While the line y equals x starts above the curve near 0, the exponential function 6 to the x over 18 has a growth rate that constantly increases. The curves cross once near 1.12, then the line pulls ahead temporarily. But the accelerating exponential growth guarantees it will eventually catch up and cross the line again, which happens at 36. After that crossing at 36, the exponential will always grow faster than the line, so they can never intersect again. This is the fundamental property of exponential functions. They eventually dominate all polynomial growth. So we've confirmed there's a second positive solution at approximately 1.118. This is a transcendental number that cannot be expressed using simple radicals, but we can compute it to any precision we need. Now let's explore what happens when x is negative. This is where things get more subtle. We need to go back to our original equation. Remember that 18th root trick we used earlier? It doesn't work the same way for negative x. Here's why. When x is negative, both sides are still positive. X to the 18th power is positive because we're raising a negative number to an even power, and 6 to the power of x is always positive. But here's the crucial point. When we take the 18th root of x to the 18th for negative x, we get the absolute value, which equals negative x, not positive x. So our equation transforms to 6 to the x over 18 equals negative x. This is a completely different transcendental equation from the positive case, and again, there's no algebraic solution. Let's visualize this by plotting both sides of the original equation for negative x values. Here we have the blue curve showing y equals 6 to the power of x, and the red curve showing y equals x to the 18th power. And they intersect exactly once in the negative region. Let's apply Newton-Raphson to find this solution as well. For the negative solution, we go back to the original equation and use Newton-Raphson with a function that captures both sides. We define g of x as 6 to the x minus x to the 18th, looking for where this equals 0. The derivative is natural log of 6 times 6 to the x minus 18x to the 17th. Starting with negative 1, the iterations converge to negative 0.9127. After 4 iterations, we have our precise answer. So there we have it, our third and final solution, computed with mathematical precision. To confirm this is the only negative solution, notice that as x goes to negative infinity, 6 to the x approaches 0, while x to the 18th explodes to infinity. So these curves can only intersect once in the negative region. Putting it all together, our complete investigation has uncovered exactly 3 distinct real solutions to this equation. First, we have our beautiful exact solution, the positive integer 36, which we found through algebraic reasoning. Second, we found another positive solution at approximately 1.118 through numerical methods. This is a transcendental number with no exact algebraic form. And third, the negative solution at approximately negative 0.913, which we computed using the same numerical approach. What I find beautiful about this problem is how it reminds us that in mathematics, the details really matter. That seemingly innocent 18th root simplification works differently for negative numbers because of absolute values. This subtle point is what separates finding one solution from finding all solutions. If you enjoyed this problem, give it a like and subscribe for more. And, as always, thanks for watching.